Thank you very much. So welcome, everybody. So good morning. Thanks for showing up for the first session. And yeah, the plan today is to continue somehow where I stopped yesterday. So yesterday, just a very brief recap, I sort of presented you this motivation to talk about tensor networks in the context of describing states of quantum many-body systems. One big guiding line is like this area law. Okay, it's a bit weak. So this area law, and then I told you about two families that say building this area law just by construction, which are the matrix product states and PEPs. I left out all the other families I wanted to talk about, but I sort of discuss a bit some of the properties that also Norbert commented on later in the day. And so the most important ones from the point of view of using them to describe quantum many-body systems would be probably this one. So in the case of matrix product states, we know they are good approximations to ground states. This is also true for PEPs, some just subtleties there. And the reason is precisely this area law that we know is true in ground states of local Hamiltonian, except for small corrections. And in the case of matrix product states, they are very, very powerful because of this reason that we can compute expectation values efficiently. And I hope to show you a little bit how to use this in practice in algorithms, so how we do really compute things with them today. And well, there's another property that I just commented on passing, which is that they can be prepared efficiently, so that if somebody gives you a description of a matrix product state, this state, and you have an experimentalist friend with a lab, then you can just tell them, okay, this is the tensors, and they can go and prepare this state efficiently, which is like these states exist somehow. That's a way of saying it, because you can prepare them in a reasonable time. For PEPs, there are some things that are different. So on the one hand, there's no way to compute expectation values exactly in general, and they can contain much more correlations than an MPS. On the other hand, this thing with the recipe and the lab doesn't hold for PEP, so we cannot prepare arbitrary PEP efficiently. But they are still, they still have this property that they are good as a tool to approximate ground states of local Hamiltonian. And well, when we say ground states, also equilibrium states, thermal equilibrium states. So from the physical point of view, it makes perfect sense to try to use these tools to describe the states we are interested in. So what I want to do today is to sort of describe a little bit the other tensor networks that I left out yesterday, to see some other possibilities, and to talk about algorithms. So which kind of things can we compute with these tensor networks, a bit how, and well, maybe some open question or some open line of research. So the first one I want to talk about is really not that different. I just mentioned it very fast yesterday, but I want to stop to comment on the differences, which is matrix product operators. So a matrix product operator is basically a matrix product state. So if you recall, the way I presented matrix product states from like the beginning was to say, okay, our general states are tensors with n legs. And matrix product states correspond to states where the coefficients have a particular tensor network structure. This tensor network structure is this kind of tensor train that, well, if we write the coefficients, has this form. Of course, this is true. Just, I mean, we can take these ansatz for any vector, right? So we can think of operators as vectors in a different vector space, which also has a tensor product structure. So we can do the same thing for operators. We can say, okay, operators so operators that act on the many-body system, we can treat also as vectors, consider them, or in our case, as tensors. In this case, they have like double indices, so the dimension is the square of the dimension we had before. And we can write it in a tensor product basis. And we can consider operators where the coefficients in this tensor product basis has actually the same matrix product state structure. So each of the coefficients can be written as a tensor train. Again, only now, the physical dimensions, the open indices that we had before, instead of just being the state of the basis, well, they are labels for some operator basis. In this case, I wrote a canonical basis, but it could be some different basis. The important thing is that it's a tensor product of, say, a basis of operators. So this is just an MPO. So it's basically, so matrix product operator is a matrix product state that describes an operator. Okay, so what kind of operators have this structure? Well, there are many operators that have this structure exactly. And one example, which is very useful for the algorithms and for what I'm telling you about, is that of local Hamiltonian. And actually, local Hamiltonians we can write as simple matrix product operators. And this is a property that actually is the same one as in matrix product states. What it boils down to is the fact that there is an equivalence somehow between this matrix product state construction and finite state automata. So finite state automata are a computational model that recognizes regular expressions, and that's precisely what matrix product state do. So this is an example of a regular expression, and this regular expression, so if we have a finite state automata that would recognize this expression, what it would accept is strings of binary strings in this case that have any number of zeros, a single one, and any number of zeros. Oh, okay. I will show it in a slide. So this is a computational model that is equivalent to, say, regular grammar somehow. Regular grammars. So it accepts regular grammars or regular expressions, regular languages. Okay, I'll show it in a second what the definition is. This is just the concept. I mean, if you ever programmed anything in a scripting language, you have used regular expressions that look like that. And this means so a character which is 0 any number of times, like no time or any number, 1 precisely once, and then any number of zeros again. So this will accept the strings. In this case, I'm restricting myself to strings of length 4 because I will think of systems with a finite system size. But in general, it could be any length. So this kind of regular expression would match, if you want, any of these strings, but wouldn't match strings like all zeros or 2 ones in any position. So this is just what the regular expression is. And of course, you immediately can see that this looks very much like the W state that we were talking about yesterday. So it's basically the same structure. So this is the structure that the matrix product state is going to produce. And, well, not only the W state, right? We can also write an operator that has this structure. For instance, any single site operator, like magnetization in this case, or sigma x in any site, which we would write typically. In this context, we don't write all the tensor products with the identities. Often, we write just a sum of a single site operator, but it means that we have the operator acting everywhere. So let me see. OK, so here comes the definition of the finite state automata. So a finite state automata is, as I said, a computational model, and is defined in this way. So you have a set of states. I call it S. And among these states, there is an initial state that I call S0, and a final state, I don't know, like maybe I'm too far. So, and a final state, which I call, or several final states, which are like the accepting states, that I call SF. There is an input alphabet, some symbols, and there is a set of transitions that allow us to move from one state to another when we receive some of the symbol. So this is just a set of allowed transitions. So the simplest example is the one, or one of the simplest examples, is the one that I just showed before. So in the example I showed before, we just have 2 characters. So the only alphabet we need is, say, 0 and 1. And we need 2 states. You will see it in a second. So I call these states B for before seeing a 1, and A for after seeing a 1. So there are 2 states, and usually these finite state automata are represented graphically, so they also have a diagram language in this way. So states are depicted like inside circles, and the initial state is marked with an arrow, so that just means that this is an initial state, and the final states are marked with a double circle, so double line in the center. So transitions are so shown as arrows labeled by the input character that take you from one state to another, right? So in this case, we can be in the initial state. The initial state is before seeing a 0. We haven't seen anything. Of course, we are before seeing a 0. And if we see a 0, we stay in the initial state. So we stay in the state before seeing a 0, right? Now, from this state, we can accept a 1. And if we accept a 1, then we move a state. Then we have seen the 1. So we move to the after state. And now we could stop. So this is a final state. But so instead of stopping, we can still accept more 0. So this is just the diagram for this finite state automaton. Of course, you can construct much more complicated ones, but you get the idea. So now how do we translate that to an MPS, right? It looks a very different diagram. But it actually is the same thing. So the input symbols are basically the possible values of the physical index. The number of states, sorry, I went a bit fast. The number of states is the size of the bond dimension, the dimension of the virtual indices. And the valid transition, so the set of transitions, are the non-vanishing elements in our tensor. So I'm just doing the sort of translationally invariant case where we just have one tensor, but I will set the boundaries in here. But you can, of course, do this with different transitions for different sides and so on. But I think you get the idea. So, for instance, in here we have a valid transition from B to B when we see the 0. So that means that in our tensors we will have a component which is non-zero, which corresponds to virtual indices B to B and physical index 0. And I'm just giving this a value 1. I'm not talking here about different weights for different components, although I could put this in the picture. I have another transition that takes me from state after seeing a 1 to after seeing a 1, again receiving a 0. So I have another element which is A to A and 0. And I give this, again, a value 0. And there are no more transitions with the input value 0. So I can already write the tensor, so the matrix corresponding to the physical index 0. So if you recall our matrix product states, the tensors have 3 indices, right? When we fix the physical index, then we can write a matrix. And this is a practical way of showing the tensor. It's not the only one, but it's a practical one. So I just write the particular matrix for physical index 0 in this way. I just have these elements. There's no more transition with 0. So this is my matrix M0. And well, I write it like this. Sorry, I forgot to say this because, okay, these are labels, right, for the states. I just assign them to some value of the virtual dimension, which in this case is the same order that I'm showing in here. And then transitions with 1, we only have 1, from B to A with input value 1. So this gives me the only non-vanishing element of the matrix for physical index 1, which will be, in this convention of writing the first component for the B and the second for A, this one. So this is the same matrices I was showing yesterday. I'm just constructing them explicitly here using this equivalence to the finite state automata. And well, as it came up in the discussion yesterday, what I was showing had no boundaries. So if I would just allow this to be, let's say, in a periodic system, I would also have the 0, 0, 0 component, which is not allowed in this finite state automata. And for that, I put boundary. So I put an initial matrix which is different and a final matrix which is different. And what I do is just ask that at the beginning of the chain, my state is always B. And at the end of the chain, my state is always A. And I can do this for a finite length. And then I've restricted my automaton to accept only strings of a given length, which is that of the system side. That's the only state difference. So what is the boundaries? Well, for the left boundary, we take the raw matrices, so the say leftmost tensor, which will have bond dimension 1 on the left, right? So it's just a row, which corresponds to the state precisely B, the initial state. And for the n, we take the column that corresponds to final state A. And that's it. So that's exactly the MPS that I was showing before, now with the boundaries and accepting exactly the W state. So, well, you can just write it explicitly now. So this is just to see the connection to the MPO. We can just write the same thing for an MPO now. Okay, one thing that I didn't say that comes here is that a different language that sometimes people use, not so much for MPS but for MPOs, is to write the whole tensor instead of writing the M0 and MO as, in this case, a vector valued matrix, where you show both at the same time. So in this case, the vector 0 means the 1, 0 vector, so column vector, and the state 1 of the basis means the 0, 1 vector. So in this language, you are showing both components of the tensor at the same time. You can do the same thing for, so if you plug in this expression in here, well, this actually corresponds to summing each of the i's with the corresponding basis element. But if you plug in these matrices in here and you expand it, you will get exactly what we discussed yesterday, the W state. You can do the same thing, changing the basis. Instead of a vector basis, an operator basis. Like In this case, we only need 2 operators, so this is not the full basis, but you don't need any more elements to appear. And instead of putting a 0, you put the identity. Instead of putting a 1, you put 1 Pauli matrix. And what you get in this way is precisely this magnetization. It's the same MPS, basically, just different in a different place. So the same coefficient for a different place. Okay, so you can do this with more complicated Hamiltonians. You can do it for any local Hamiltonian, just making it a bit more complicated. And the Ising Hamiltonian is sort of like the test bench for anything that you want to do in this field. And it is a bit more complicated than the operator that I showed before. So it contains also a nearest neighbor term. So you have a sum of 2 body terms that goes over the whole thing. So how do you include this in the automata picture or in the MPS description that I showed? Well, the only thing you need to realize is that you need one extra state, because when you move from one side to the next, you need to know if you are before seeing anything, after seeing everything, or in the middle of precisely this term. So if you just accept a sigma set, say, the next move has to be accepting another sigma set, and then you are done. So this requires one extra state, and so one extra virtual state, and that means one more in the bond dimension to describe the MPO. And well, you can check that this is an MPO description of this Hamiltonian. You can do this for any local Hamiltonian, for spin 1/2 models, for nearest neighbor Hamiltonians. It's enough to have bond dimension 5. All of them can be written exactly that way. So this is, say, an interesting set of matrix product operators. Well, okay, these are the boundaries. Again, here the logic is the same one as before. You, at the beginning of the chain, you ask for like being in the initial state. At the end, you ask for being exactly at the accepting state. Okay, so this is a set of MPOs, as I was saying, that is very useful to study quantum many-body problems, because we are interested in Hamiltonians that often have this expression. And there are some that do not have this expression. For instance, if you have longer range interactions, then you need larger and larger bond dimension to take care of that, except in some exceptional cases. But what you can do very often is to use approximation. So you can still approximate your interesting model as a matrix product operator. And this is extremely useful for the algorithm. But there is another whole set or another whole use of MPOs, which is not describing exactly local Hamiltonians, which is using them as an ansatz for states too, or even for operators, right, for more general operators. But let me talk about states, because I'm talking about quantum states these days. So if we want to describe mixed states, we can think of mixed states, so density operators, that have the structure of a matrix product operator. And that's just what I'm showing here. Again, the same picture. It's just states where the coefficients in a given tensor product basis have the structure of an MPS. But the problem is that this worked without any concerns in the case of pure states, because for a pure state, the only thing we need for it to be a valid state is that it is a vector, normalized vector in the Hilbert space. And we can always normalize the vector. So if we get something else, we can actually, with the canonical form, we can ensure that the thing is normalized all the time. But this is not enough for density operators. For density operators, we need that they are Hermitian. We need that they are normalized, so that the trace is 1. And we need that they are positive. And then, among the MPOs, not all the MPOs will have this property. So the main question, if you want to do things efficiently with tensor networks, is whether you can impose these properties in a local way. And in a local way means looking at tensor by tensor, basically. So Hermiticity is not that bad, because what does it mean that the state is Hermitian? Well, it means that it's the same if you flip the indices and complex conjugate. So you could just ask that tensor by tensor, it has this property, and then it would ensure the property. That would be one way. But you can also, as no, I didn't say it, but I forgot to say it. So you can also take the state and its Hermitian conjugate and add them together. And although adding two MPSs doesn't give you an MPS with the same bond dimension, it gives you an MPS that at most has twice the bond dimension. So you can always add the blocks, say, so put the two blocks together, and then you get a bigger tensor. And that's still efficient, because, okay, you multiply the bond dimension by 2. You might not be happy if you are doing numeric, which is very demanding, but it still works. It's still efficient, and that's fine. So in a sense, that's a benign property to impose. So the normalization, you want to ask that the trace is 1. And the trace, you can immediately compute in here. You just trace side by side each of the elements in the basis, and you get a number. So computing this number is an efficient problem, say, it's an efficient question that you can solve efficiently, I mean. And as far as you don't have an operator that is traceless, then you can normalize your operator. So it's still okay. But positivity is a whole different story, of course, because we cannot impose positivity at the level of tensor. And actually, Gemma, for instance, has worked on that, and also Jens. It's a very hard problem to, if you are given the tensors, to know whether the MPO that you get out of it is positive or not. So that seems to be like a not so good situation for numerics. Fortunately, there is some way in which we can also work with valid MPOs for states. And that's that of purification. So what is a purification? So a purification, given any quantum system, say S, and we have a mixed state rho S, we can always find a pure state in a larger system such that when we trace out the extra auxiliary system, we get back the state we want. And this pure state in a larger system is what is called a purification. How do we find it? Well, it's quite easy to see that this exists, because if we look at the spectral decomposition of our initial state, which is a mixed state, then we can invent an auxiliary system, which is larger. Larger is the total is larger, so the auxiliary system needs to be at most as large as our system. So, and then we write a pure state of system plus ancilla, which has as coefficients precisely the eigenvalues of, well, the square root of the eigenvalues of our density matrix. And basically what we are doing here is taking for states, so for this decomposition, for each state on the spectral decomposition of our system, one state in a basis of the auxiliary system. We label with the same index just to keep track. But what we need is as many orthogonal states in the auxiliary system as states we had in the spectral decomposition, so at most as many as we had in the basis of our initial state. And this is a purification. And you can immediately see that if you trace out the auxiliary system, this is just an orthogonal basis, so we just get the same initial state with the proper coefficient. So this is a purification. So how does this work to build an MPO that works? Okay, so one thing that I didn't say in here is important, but I'm not gonna stop in there, is that this is basically defined up to any change of basis that we want to do in our auxiliary system, because the only thing we need is that these states are orthogonal to each other. We could choose a different basis, and this is completely free. Okay, so we can work with the purification. In which way? Well, we can think that our purification has a matrix product state structure, because we know that any matrix product state is a valid pure state, and then we will have a valid density matrix coming out of that. For it to have the MPO structure, what we need to do is to choose the, say, structure of entanglement between system and auxiliary system in a certain way. So what we do is for every site in our chain, so for every system site, I think systems here are blue, I don't remember now, we put an auxiliary system of the same dimension. So we could have chosen a purification differently. We could have said, okay, this is my system, and then I continue the chain with the ancilla. But this is not the construction in here. So you say one side of the system, one side of the ancilla. And for this basis, so this sort of ordering of the degrees of freedom, you choose an MPS. So you assume an MPS form. You put this answer for the purification. And once you have this, well, the reduced density matrix is computed by, you take the ket, you take the conjugate, the bra, and you trace out, oh no, sorry, the ancillas were the blue ones on the left now. So you trace out the ancillas. And now, of course, you have an MPO structure where each of the tensors would be this double layer thing, so that it has some structure. So of course, it's not general anymore, because you need tensors to have this structure. But it is positive by construction, and it's a valid MPO. And this is the purification, local purification sometimes it's called, and it can be used in the numeric. Okay, so the same as in the case of pure states, in the case of an MPO, the bond dimension is also what limits the number of parameters. The difference is that now we have basically a local dimension which is squared, because we are dealing with operators. but there is so some subtleties in here. So in the pure case, we were saying the Schmidt rank, basically the number of singular values across one cut, was related to the entanglement in the state. So now it's also true that we have a Schmidt rank in this decomposition. We still have a vector, so we can do the same singular value decomposition, and it is still the crucial thing to know whether our operator is written as an MPO or not. But this is not entanglement anymore. People have defined this as operator space entanglement entropy because it's completely analogous to entanglement, the quantities that you get in there, but they do not mean entanglement in the same physical sense. But it's still the crucial quantity, or one crucial quantity, to know whether an operator has this form or not. How do we compute things with these MPOs? Well, they are MPSs, so we can also compute expectation values efficiently. The difference is that when we want to compute expectation values in a density operator, we take the trace of the operator times the density operator. So in this case, we don't double, we don't have a sandwich of the MPS with itself. We have something like this. But if we are working with the purification, then we get back to the same picture because we can just reshuffle things, and then we are basically computing an expectation value of an operator, which is a tensor product of whatever was acting on the physical side times the identity on the ancillary side in normal language. This, of course, you can see that it's very natural to work with this purification somehow in the algorithms, because basically the same thing we were doing before with matrix plus thing. But one can also work directly with the MPO description. Okay, so this is basically what I wanted to say about matrix product operators, which are matrix product states except for these subtleties or these differences. But I wanted to show you some of the other tensor networks that do not fulfill the area law in one dimension. And that's precisely the motivation for people to introduce this three-tensor network or this meta. So the idea is that matrix product states work very well in practice. They are very powerful for the numerics, but we know that they have exponentially decaying correlations. So which means that they cannot describe exactly, they cannot capture exactly the kind of correlations we have in a critical system, because those have logarithmic corrections to the area law, and they can have more entanglement. So one idea to go beyond that was these three tensor networks, which were introduced by Guillaume Vidal and co-workers. And the idea, well, the name is self-descriptive, right? So it's that the network has a tree structure. This is just a picture with a binary tree, but it could have any other structure. So what is important in here is that, on one hand, it is possible to contract them efficiently. And this is true for any tensor network without loops, basically. So if you want to compute local observables, in this case, you basically end up with a tensor network without loops. You don't have the problem I described yesterday for PEP, and you can contract them efficiently. And actually, you can define them just made out of isometries, such that you can also impose sort of a canonical form where everything is normalized. And well, this is an example of how would you compute an expectation value of a local observable. So okay, maybe I should have stopped to say that in this picture, for instance, my open indices that were pointing down were the physical indices, that would be the size of the chain, and all the other tensors, so going up, they do not have any open physical index. Okay, they just have virtual indices, and they sort of implement a real space renormalization of my chain. So I'm like throwing away degrees of freedom as I go up in these levels of these steps of renormalization. But anyway, so if we want to compute an expectation value at the level of physical indices, something local like this circle, which would be a local operator, you need to contract with the adjoint. You get something like this, and then immediately you can see that if you are imposing these isometries, each pair of isometries say gives you an identity, and then you can go like simplifying these blocks, and at the end you end up with something which has a finite width, say, to contract, or a constant width to contract. And that's the reason why you can do this efficiently. The same is true if instead of just looking at the expectation value of an operator, you look at the reduced density matrix. And if you look at the reduced density matrix, for instance, for these sites in here, you can just write it like this by doing exactly the same game, tracing out over all the other indices. And now you can say, okay, what is the rank of this reduced density matrix? And you can see that it can be upper bounded by like the smallest number of legs that you need to cut in here. And this gives you an upper bound for how much entanglement you can have in this tensor network, because this is giving you an upper bound of how entangled this part of the system is with the rest. Okay? The same as before in the MPS, we had to cut two legs only to split one part of the system from the rest, or in the PEPs, we have to cut everything around. Well, in here, we have to cut, in this case, for this very small system, you have to cut only two. So if you do this in general, you can see that it's not the same depending on which sides you choose, because this is not translational invariant. For some, say, if you think of 4 sides, you could pick up these two, and then you only need to cut one leg, right? So this is like an MPS. But it's not true for all of them. So you can choose these ones, and then you will see that you need to cut a logarithmic number of legs with the size of your subsystem. So although not in all cuts, it can be a number. So this is like the bound of the entropy. It can be logarithmic in the number of sides of your subsystem. So you can have logarithmic corrections to the area law. Of course, it's not in every cut, but in average, you can make it that it is like that. For instance, like summing several trees. And then you have a way to describe critical systems that have the right that doesn't have, sorry? No, yes, you can choose any other kind of tree. Yeah, the important thing is that this is a tree and it has no loop, but yes. Okay, yeah, correlations can decay as a power law, like it happens in critical systems, because you can hold enough, say, entanglement in this case. Okay, one interesting thing is that, well, here it's drawn in a one-dimensional fashion, these sides, but of course, this can be around a circle, or it can be on 2 dimensions and still put a tree on top. So this ansatz works directly in 2 dimensions for periodic boundary conditions. But in 2 dimensions, I will say it a bit later, then you don't get a correction to the area law in 2 dimensions. Okay, and this I already said that you don't have loops, and this makes it easy to compute. But okay, if you want to see which kind of states you can describe in this manner, or you can renormalize with this kind of structure, you might think, okay, which kind of correlations can I remove with this isometry? And you can imagine a state which has just short-range correlations like this. So what happens if you, to this state, you apply this kind of transformation, or in other words, you want to create this state with this kind of network. So say that you want to choose the tensors such that they prepare this state. This state is just short-range correlations, okay? This is sort of the easy state to prepare in a MPS form. So the question here is, can you do this also with a very small tree, or what happens in here? And well, you can see that these short-range correlations that correspond to these isometries that directly act on a pair, you can sort of remove at the first level, or create with just one level of isometry. But of course, there are the correlations that are in between 2 of these steps. And they have to go 1 level up, and so on. Because, of course, if I do that, I still need to put in these correlations. So either from the point of view of removing the correlations or from creating them, you see that short-range correlations translate into very long range in the renormalization, because the higher up we go in this renormalization tree, the longer range things we are describing. So this is sort of a problem if you want to remove short-range correlations with 1 layer of the tree. And the solution to that was the MERA that was introduced by Geoffrey Vidal in 2007 or so. Where's the reference? Okay, the reference will appear. And you see that, so the solution for that is, or at least one solution for that is, before applying these renormalization steps in which you throw away degrees of freedom, you apply a unitary that tries to disentangle precisely these sides that you are then moving to longer range scale in the next step. And these layers that appear here in green are precisely these, they are called disentanglers. Disentanglers, they are unitary transformations that try to minimize, for instance, in here, try to minimize the entanglement between these 2 sides. How would this solve the problem before? Well, the way it would solve the problem before is that, in this case, these unitaries have the power to, say, transform a product state or map a product state into this maximally entangled pair. And then in one layer, you sort of can describe this kind of short-range correlation. Ooh, good question. I don't know, probably, because, well, MPSs are included in trees, so for sure, yes. But I don't know if it has actually directly more power. I mean, it's bigger than MPS, than with a given bond dimension, so it must be more powerful, but I don't know in the language of automata if people have looked at that. I think it's a very good question. So, okay, yeah, from the point of view of computing things with them, these tensor networks have loops now. But because they are so special that they are made out of unitaries and isometries, we can still compute some things efficiently. And the things that we can compute efficiently are, like, well, for instance, in here is the norm, but also like local operators. And the reason is precisely that, well, these unitaries say we can compute the expectation value of a local observable. These unitaries will cancel out, the same as the isometries and so on. And okay, so the operator disappear for some reason. So what you end up with is that for any local operator, what you have to contract is, okay, you have this tower of tensors, it's called a causal cone of the operator, but it has a bounded width. It doesn't grow larger and larger the higher up you go. So if you look at the other question that I have been asking, so how much entanglement, so how much does this violate the area law in one dimension? How much entanglement can we have in a subsystem? Well, you can see that in this case, because there is a much more regular structure, so this is just a very small picture because drawing Mera is a bit tedious, but you can convince yourself of making a larger picture that this is the case, that you always have an upper bound on the entropy given by the number of legs you cut. That goes like the logarithm of the number of sides that you include in here. So again, well, this is the reason why this thing can describe critical systems in one dimension very well. However, and sorry, I didn't put the reference in here, Jens and co-workers, they proved that in 2D, if you can put the same structure in 2D and in 2 dimensions and describe a 2-dimensional system, and then it is a subset of it, so it cannot violate the area law in higher dimensions. Yes. Yeah, you put them in between. So at each level, you put a layer. Yeah, sorry, this is a too small example. You put it at each level before applying the isometries that actually throw degrees of freedom away. So yes, exactly. So each step in this procedure, which is also a renormalization procedure, is one layer of disentanglers and then one layer of isometry. Okay, so yeah, for the rest of the talk, I want to tell you about which kind of things we do with these algorithms in the numeric, right? What can we do with tensor network states? And well, that regards practical calculations. So in a very simplified way, so a bit simplistic, but it's quite true. We have 2 main types of algorithms, which are really like the workhorse of like tensor network calculation, tensor network states calculation. So one of them is a variational optimization. So this is mainly used for finding ground state. And on the other hand, there is the possibility to take one of these states in one family, apply some local operator, or maybe not so local, and so approximate the result again in the family. And this is really the basis for time evolution algorithm, and not only time evolution. So, okay, how does this variational minimization of energy work? Well, the variational minimization of energy is really like the DMRG algorithm that I mentioned yesterday. So the idea is you have a Hamiltonian, typically a local Hamiltonian, and you want to find the ground state. So when I say local Hamiltonian, for instance, this would be a hybrid picture of a nearest neighbor Hamiltonian, where you have a sum of identities tensor, some 2-body operator. But in general, I'm thinking of a Hamiltonian that you can write with the structure of an MPO, as I showed before. So this is, of course, all the local Hamiltonians, but it can include other Hamiltonians. And what we want is an approximation to the ground state, which has the structure of a matrix state. you can do this also in PEPs. It gets more complicated, but the idea is the same. So I'll just show the one-dimensional picture. So the algorithm tries to use the variational principle so that the lowest, so that any state we find will give us an upper bound to the lowest energy. And then we try to minimize precisely the expectation value within the set of states that we are interested in. And the set of states we are interested in this case, is, say, matrix product states with a given bond dimension. So how does this work? Well, if you want to do this in the finite case, where each of the tensors is different, this gives you a very non-linear minimization if you want to minimize all the variables at the same time. So the way it is done, like the standard way of solving this problem, is called an alternating least squares approach, where what you do is to optimize one tensor at a time while fixing all the others. So how is this possible? So this is possible because the quantity you want to minimize is this ratio of the expectation value of the Hamiltonian with respect to the norm, and both things can be computed as tensor networks. So the expectation value of the Hamiltonian will be a tensor network like the one that is shown in here. The norm, the denominator, is a tensor network like it's shown in here. And so for this alternating least squares strategy, what we do is that we consider all the tensors but one as fixed. And say this is the tensor that we want to vary, so all the rest is fixed. So we write the whole thing as a function of this tensor that is our variables now. And then you get an effective Hamiltonian, which is really just the contraction of the rest of the tensor network, except for this side, and an effective norm, which is also the contraction of the denominator except for this thing. And the way it works is that you solve this local problem for this tensor, and you sweep back and forth, repeat for of the tensors until the thing converges. So this is really the DMRG algorithm. So the solution of this local problem is, of course, a generalized eigenvalue problem. So you'll have to look for the lowest generalized eigenvalue of this this effective Hamiltonian. And in the 1D case, you can take advantage of the fact that there is a canonical form and the fact that that there is a structure in these things that you are contracting to make the thing more efficient and actually remove the effective norm and so on. This is actually what the DMRG algorithm is doing. And you get a cost that scales only like the bond dimension to the cube, which is very efficient for this math. And it means that you can exploit this to compute tensors with like thousands of bond dimension. And well, the algorithm has some guarantees, like for instance, because at every step you can only improve your energy. So the energy is just decreasing, or it will stop at some point, because the energy of the Hamiltonian is lower bounded, so it cannot go down infinitely. You can also do it in periodic boundary conditions, and it has a higher cost. And you can modify things to also deal with not only the ground state, but also excited state. So you can do all these things in practice. You can integrate symmetries, as Norbert was telling about yesterday, and this gives you more power in the algorithm. And you can do the whole thing for PEPs too. What are the differences? Well, you cannot compute exactly this norm or this Hamiltonian, because these are contractions in the two-dimensional case, but you have approximate manners of doing this, and you can control the approximation that you do in this step. So you can just perform the whole thing, and this is actually what the most powerful PEPs algorithms are doing nowadays. Yes?
Yes, so you know when you run the algorithm, when you have a Hamiltonian, do you know how big it is, or do you do this on the fly, or what?
You have some ideas, okay? Because of the arguments that I gave yesterday about if you know properties of the Hamiltonian, you know that there is some cases where you have an efficient approximation, and you need that. You, for instance, know that it might need to grow polynomially with the system size, or that it doesn't, but you don't know the number.
It's like a parameter. You choose it.
Yes, yes. So in practice, you choose a small bond dimension, and then you go increasing it. Since you know that the larger and larger bond dimension will include your solutions before and will only improve the result, this is a trick that people use to look for convergence until some value. So you put a predefined precision, exactly, and then you run until this is met, or maybe until you cannot run with higher bond dimension. And then what people do, especially in PEPs, where it is much more costly, is to use extrapolation. You can extrapolate in bond dimension, especially in critical systems. This has been studied, how things. So there's like finite size scaling. There is a similar thing in finite entanglement scaling. So you can also extrapolate in one dimension to make the algorithms more, so the results more powerful. But okay, but in PEPs you can do the whole thing with the approximations in the contraction, but even like that, you get a scaling that goes like d to the 10. And d to the 10 is much more costly than d to the 3, which explains why in PEPs it's much more difficult to reach large one dimensions. Although, of course, your tensors are very large because they have 4 legs now, so you have a large number of parameters even with small one dimensions. Okay, I wanted to show an example of how this works. So the Ising model that I showed before. So this is just to give you a flavor of how this algorithm works. So this Ising model, we know that it has a critical point when both coefficients, both terms are equally large. And for instance, for a chain of 20 sides, which has a dimension of the Hilbert space 1 million, the largest one dimension you would need, according to this reasoning, that any state in the Hilbert space you can describe with a given MPS with a one dimension that goes up to d to the n halves. Well, the one dimension you would need at most would be 1000 for this system, whatever the state you want to describe. Now, this kind of problem you can just solve in your laptop. For instance, with MATLAB, I ran this with MATLAB. You have a function with aix, which gives you eigenvalues of a sparse matrix. And it gives you what is the lowest energy in here. In my laptop, it took like 40 seconds to 38 seconds. Now you can do the same thing with matrix product states. And well, this is sort of an example of the output of a program. So you initialize the same thing. You start running C for bond dimension 10. And well, it gives you some eigenvalues. So this is the energy per particle. So it's divided by the number of particles. So you get a number here, which is, I mean, it's probably small, but it's quite similar to this one. And it's similar up to, I don't know, 6 or 7 digits already with one dimension 10. And of course, to, oops, sorry. So I just wanted to say that if you increase the one dimension, you basically, in this case, you see that you are converged in here, because yes, the changes in here are probably just compatible with numerical errors that I'm doing in this algorithm. Now, of course, this is so not such an interesting situation, because even though I'm choosing the critical values, this is a very small system. It's only 20 sides, so there's still an energy gap and everything. So you can just go to a much larger system. So now you take 200 sides. 200 sides, the dimension of the Hilbert space is 10 to the 60. There's no way that I can solve this, the laptop. So, and the bond dimension that I would need at most would be 10 to the 30. But we can run the same game. And again, you can see here the results starting with one dimension 10. You have some value of the energy. We know in this case what is the exact solution for the thermodynamic limit, so I could have written it there. It's very close to that. I forgot to write the number. But what you can do is to check what I was saying before. You can check what happens when you increase your one dimension, and then you refine your result more and more. And you see that already with one dimension 10 in here, you have already like 5 or 6 digits converged. And the time it took, I didn't say it before, this was 8 seconds, and then 16 seconds for the next one dimension. So this sort of gives you a flavor of why it is a powerful tool to have, because you can deal with these large systems in quite an efficient manner. Yes?
So you told us about the complexity in D. How about the in
It's polynomial in N. So every sweep is basically like linear in N, because you go once. Right. What you don't know beforehand is how many sweeps you're going to need to converge. And that depends on, so there have been some studies about that, but it depends on the properties of the problem. For instance, if it is gapped or not, if it is critical, it's much harder, and also the density of states you have in there. So there's some, say, pathological cases where you might have, for instance, many metastable states which are very close in energy, and your algorithm might tend to get trapped in those and might need many, because the sort of the weakness, if you want, of the algorithm is that it only goes making local changes to your tensor. So if you need a global chain to go down in energy and get close to your ground state, it will take you a long time to be able to do that by just looking at the local properties. So there is not a definite answer to this. It depends on the properties of the Hamiltonian. Okay, so the other kind of algorithms that are around, there are more, but these are like the basic ones, the best established ones, the ones that you can actually, at least for the one-dimensional case, you have open source implementations around that you can just download and use on some different problem. So this, the other big set of algorithms would be approximating the action of some local operator. Yes. Yes. Infinite. No, you can work directly in the thermodynamic limit with an ansatz which is translational invariant, so that you only have one tensor. And then you can formulate a variational algorithm for that, or you can use this algorithm directly that I'm going to tell you. This is actually the easiest way, and that's what people have mostly used for the thermodynamic limit. But there is also the variational algorithm. Yeah, you can work. And you can not take one tensor, but take a unit cell and repeat it to be more, so to allow more variational parameters. So this set of operations would be the result of, you have a state. So here I'm just showing a little bit of an MPS, and I apply a two-body gate. This is pretty general situation, because even if we have a two-dimensional case, like PEPs or so on, if we are looking at a local Hamiltonian, we will have this kind of nearest neighbor terms in the Hamiltonian, or we might want to simulate a quantum circuit where we have gates that act on two sides. So this is like quite, this situation occurs quite often. And then the goal is, after applying something, of course, now you have like a bigger tensor, which doesn't necessarily fit in this structure of two tensors with a given bond dimension. In general, it has increased. So the trick is how to reduce the bond dimension again to find an approximation to the result. And this can be done at the local level, or it can also be done like in a more global way when you act with something which has the structure of Q, and you allow all your tensors. Okay. And although not the only way to do time evolution, this is really the basis for simulating time evolution, the most common algorithm. So how does this work? The easiest one is this local truncation. This is really the basis of this TBD algorithm, which is time evolved block decimation, what it means. And that's really the core of the algorithm, this truncation after applying some local operation. So how does this work? It's pretty simple, and I would say it's like if one wants to implement one single tensor network algorithm, that's the simplest one to implement. Because you see, well, the way to implement it in the simplest or most straightforward manner goes back to the canonical form, or makes use of the canonical form. So if you recall the canonical form of matrix product states, somehow what I presented as the canonical form is that you can choose your tensors such that they are isometries in some direction, and in the other direction they have this fixed point which is a diagonal, but this diagonal is really like the Schmidt values across each cut. So instead of writing them in that way, which means somehow that your tensors encode these Schmidt values inside, you can just keep them explicit. So you can split your tensors in the Schmidt values, like if you would split this in half, right, and you would multiply the inverse, this thing in here, you would still have the identity property in this one, and you could keep these tensors, these lambdas, I was calling them yesterday, separate. And that's what you do in this canonical form, where instead of one tensor, you have two per side. And these two tensors, one of them is really, these gammas really contain this isometric property, and the lambdas contain explicitly the Schmidt values. And well, you can keep this explicit, and now see what can you do, like what is the simplest thing you can do to see the actions, to approximate the action of a local operator on this kind of structure. Well, the simplest thing you can do is to say, okay, let's approximate the result by just changing the tensors on which this gate is acting directly, okay, and not change any of the other tensors. What I've done in here by like removing the rest of the chain is really nothing. So I still have like the whole state of the chain in here, because what I removed was just an isometry from this virtual degree of freedom to all the physical degrees of freedom on the left, and the same on the right. So this is somehow my state written in some virtual basis for this side, virtual basis for this side, and the physical indices in here. So what is the best? So okay, I can now contract this whole thing and get a bigger tensor, which now expresses my state in this basis after acting with the local operator. And now, to reduce this to MPS form, well, I do a singular value decomposition. And then I get new Schmidt values across to this cut. And because I included the Schmidt values in here to have the whole state, if I want to recover the state before, I have to undo this transformation to recover my lambdas. That's just the step to get back to the form I had before. Okay, and so far, how many values do I have in here is just as many as I get from this singular value decomposition. So the trick, the truncation step, is reducing, so cutting this number of singular values to only the say, capital D largest one. So I want to have an MPS with one dimension capital D. This same operation works directly like that in the thermodynamic limit. So for the thermodynamic limit, if I have a nearest neighbor Hamiltonian, I could take an ansatz for my MPS that has two types of tensors, AB, 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 AB. And then I either act on even odd, or I act on odd even, if I'm doing a nearest neighbor set of gates. Say. And then I can do this side by side. And I'm working directly in the thermodynamic limit. And I will do time evolution or imaginary time evolution, as I will show in a second. Okay, the other possibility, of course, is to say, after this local operation, or after a more general operation, I allow all my tensors to change. And in principle, that can only be better, because I'm including the case before. And this would be like a global truncation, and in this case, I can optimize the distance between my resulting state and the approximation, and do this in completely analogous manner to what I showed before for the variational case, like changing my tensors one by one. This is another way of doing the same thing. So not so important. The other thing is easier to implement because you only have to keep track of modifying two tensors at a time. Anyway, this is, as I said, the basic ingredient to do time evolution with this kind of state. And how does it work for time evolution? Well, for time evolution, the way it works is you start with an MPS that has this form. And actually, I would say this is probably the first big new algorithm that came out of recognizing that this DMRG algorithm so this tensor language was useful to describe this DMRG algorithm. I think this was like the first big new thing that people realized how to do with the language. So this is why very soon after these tensors, these decompositions appeared, this was called time-dependent DMRG, but it's basically the same thing. Essentially the same thing. So, okay, so how does time evolution work? Time evolution, let's say that we have a constant Hamiltonian, which is local, like one of the simple Hamiltonians, like the one I've been showing before. And then you want to apply to our state the evolution operator, which is the exponential of the Hamiltonian. And then, of course, the exponential is not local anymore. It contains, like, you write the Taylor series for that, and you have all kinds of powers of the Hamiltonian. So you will have interactions of everybody with everybody because you have products of each term with each other as many times as you like. So this is totally non-local in general. The trick is to discretize time, so do small time steps, and then you break your evolution operator into small evolution operators, which are still non-local because they are still exponentials of the Hamiltonian with just a smaller prefactor. But each of these exponentials is now approximated. And the way it is approximated is typically by what is called a Suzuki Trotter expansion or approximation, in which the exponential of the sum of operators that do not commute with each other is approximated as a product of exponential of each of the factors. The simplest approximation is like the first order one, is just you take your Hamiltonian is the sum of two parts, and the exponential you approximate as the product of the exponential. So which parts you choose? Well, in here, what you want is to, so what you typically do for a nearest neighbor Hamiltonian is the following, you will see why. You take a part of the Hamiltonian which acts, say, on the even link. I'm labeling it with an E. And that would be, for instance, these purple boxes in here. And the other part of the Hamiltonian would act on the odd link. Of course, these two do not commute with each other because they overlap. But within each of them, each of the terms commutes with each other. So the exponential of the HE or the HO is actually a product of exponentials because these terms do not act on the same side, so they do commute with each other. So what you do is this approximation in which one step of the evolution for a small time step you approximate as a product of one of the exponentials times the other. And in tensor network pictures, it looks like something like this brick wall construction. you can actually write it a bit more generally as MPOs. Well, we can split these gates with singular value decomposition and so on. And we might find other approximations that are not exactly like this, but in general, we can just write an MPO with a finite bond dimension for one of these steps. And well, this is the basis. Now you have to apply one evolution step to an MPS, and this you can do either gate by gate using the local truncation that I said before, or like with one MPO step as this global truncation. And you do this once, and then you have your time, so your one time evolution step in your state, and so on. So you basically, this step is called truncation when you approximate the result by an MPS, and you iterate that, and you have an approximation of the result with an MPS, and after enough time for your evolution, whatever you wanted to simulate, you can compute observables because now it's an MPS and you can compute things efficiently. So this works for real time, and it works for imaginary time. So imaginary time means that these exponentials, instead of writing e to the minus I t h, I write e to the minus some tau h. And what this does, or what this is good for, is finding ground states again and finding thermal equilibrium. So if you just have this algorithm that I mentioned before with a local action, you can already compute ground states of Hamiltonians without implementing a variational cell. The way it works is the following. So if you start with an arbitrary state, say this phi 0, and you apply this real exponential, now what it does is that it basically projects onto the lowest energy state. Because if you write your state, which is an arbitrary one, as an expansion, so a linear combination of states of your energy bases with some coefficients, now when you apply the exponential of the Hamiltonian, you are going to suppress each of the terms with exponentially fast with its energy. So what you are going to be left at the end is something that is proportional to the lowest energy state, except for some normalization. So you can use this to iterate this procedure and apply imaginary time evolution. Imaginary time evolution you can write as this kind of Throttle expansion that I was showing before, and apply it gate by gate and wait until convergence. And when you have converged, then you will be, say, close to the ground state. And if you do this in practice, you see plots that look like this. For instance, in here, this would be this imaginary time, the horizontal axis. The vertical axis would be the energy per particle. In the same case I was showing before, and actually this was computed in the thermodynamic limit. So this is really an infinite system. And you see how the energy approaches the ground state energy, which is this green line, which in this case, because it's exactly solvable, we know that we can benchmark everything. And if you go into the detail, you can see this is just a zoom of the same thing. And okay, the exact value, okay, this is just the error. So the exact value is not shown in this inset. This is just the error with respect to the exact value. And you see how the error is decreasing with time. And what you have in here is different cases. Like the yellow one is a larger bond dimension and a smaller Throttle step. So the Throttle step is somehow how you discretize this exponential. The smaller you make it, the better your error, right? So if you decrease your Throttle step, you get closer to the true result. And this is what you do in practice. So actually, I should have used another. Sorry? The horizontal is the time, so imaginary time. No, 10 is the prefactor of the Hamiltonian. So the Hamiltonian in this case had a j equal 1. So it depends on the dt in here, which is a Throttle step. So it's t divided dt. So it can be 0.5, so that it will be 20, or it can be 0.02, 5 times. Or yeah, smaller. 5. Mm-hmm. Yes. Exactly. So yeah, you can make it as small as so. Okay, what I wanted to say that I didn't show in here is that typically what you do is you do one of these runs for some time step, maybe a large one, and then you decrease your time step, and you will see that your curve converges again closer and closer to the ground state. And you can also, there was a curve there, but it's not really visible in there. You can change the order of this Throttle approximation and make it more precise for the same Throttle step, and then you get also better results. So there are some tricks that you can play to get better results. Sorry? Okay, because the one I showed is really first order, which you say the exponential of the sum is the product of the exponentials, but you can just write the exponential of the sum approximated as a product of exponentials with more factors, and then you can play with the prefactors of these exponents such that you reach the desired order. So like the sum of exponentials is correct to the first order in the Taylor expansion, but you can put more factors and choose the order you want. And then you have it's a more complicated step, but it gets better precision for the same width. So people never use the first order actually in practice. At least you use the second order, which is basically as cost in the numeric. Okay, this is for imaginary time. So this, I just gave you a way to do the same thing I was showing before with the variational method. But you can also use it for real time, which is really interesting from the physical point of view. We want to understand what happens under out of equilibrium dynamics. So we want to have a state and then evolve it in time, because there are very few methods that can do real-time evolution in general. But the problem is that if you do out of equilibrium dynamics, entanglement can grow pretty fast. And if you do the simulations, this is just like again an example with the Ising model. For instance, this is like you start in a product state, you start evolving with this Hamiltonian, and this is now real time, and this is the expectation value of a local observable. Again, this is an infinite chain. So the solid line in here is the exact value, and the different color lines is what you get when you do the simulation with some fixed bond dimension. And you see that it follows the exact very well, and then suddenly it just deviates completely and gives you something completely useless. And you increase the bond dimension, and the result just holds on for a little more time, and then it goes up again. So what is going on there is something that is well understood in the one-dimensional case. And the fact is precisely that your MPSs describe states up to some entropy, and if you have more entropy than that, then, well, it's not enough. And it is known that in these kind of situations, which are called global quench, you start with this kind of easy state, and then you switch on a Hamiltonian, and even though the Hamiltonian doesn't look very complicated because it's just local and so on, the entropy can grow linearly with time. And if the entropy grows linearly with time, because we know that the MPS only holds entropy that goes as logarithm of the bond dimension might need to grow exponentially with time. And that's, of course, very bad, because in this completely random picture, if this is the time you want to simulate, this is the bond dimension you need, and this is the maximum that you can put in your computer, it means that for some time you will be, so this is really an exponential, for some time it's fine, and at some point you hit this limit. And even if you, say, double your bond dimension now, and because you buy a larger computer, you cannot reach much longer time. And this is really what you were seeing in the plot before, that you increase your bond dimension, but the time you gain is just a little shift. This basically limits the simulation of out of equilibrium dynamics if you want to describe the evolved state as an MPS. But still, we can simulate many situations. So we can extract many so physics from many interesting problems, and there are several reviews around where more sophisticated methods exist and are used, and actually physical results can be extracted in closed and open quantum systems. Especially if our situation is not that out of equilibrium, then the entanglement doesn't need to grow like that all the time. So there are situations where it doesn't grow that fast. Okay, so there are some situations, as I was saying, where we can use these techniques, these methods, without these concerns. And one of them concerns, again, these mixed states, these descriptions of mixed states, and in particular equilibrium states, which are like thermal equilibrium states. So in general, for mixed states, we can think of very similar problems to what I was saying. So we have equilibrium states, which would be thermal equilibrium states, or maybe something a bit more general. And this we can find with imaginary time evolution. I think I will show it in a second. But we can also think of time-dependent problems, which could be, again, real-time evolution, might have the same problem as before. Or it can be, evolution under dissipation. So the evolution of our open system might be given by a master equation of the Lindblad form, and then we can just compute the evolution, so simulate the evolution under this kind of equation of a mixed state. So this is also fits in the framework of doing it with tensor network. So let me talk about thermal states, which are like a very robust thing that we can do with tensor network, because we have formal results telling us that tensor networks are good approximations to thermal equilibrium states of local Hamiltonians, and we have the algorithms that are efficient and work very well to get this approximation. So a thermal state is a Gibbs state of a local Hamiltonian, and it has this form. So it's the exponential of a Hamiltonian with a factor which is the inverse temperature. So this beta here is the inverse temperature. So if we want to approximate this with a tensor network, say in the one-dimensional case with a matrix product operator, we can really use the tricks that I was showing before with imaginary time evolution. And these references in here are the ones that tell us that this is a good idea because we know that there are good approximations as say, MPOs in this case to this state. So the trick is just applying what I said before. So you apply a Throttle expansion for this exponential, which now is imaginary time, but not for infinite imaginary time, just for a given amount of time, which is the inverse temperature. And you throttlerize this by making small steps, and each of the steps you can approximate. So when I write it in this way, what I'm somehow saying is that this exponential, because I explained how to apply the exponential to an initial state, not how to do the exponential on its own, like an operator. So I can just use the trick of applying this exponential onto the identity. The identity is an MPO, which is just a product of identity. So it's a very easy MPO. And actually, I can vectorize it and treat it as an MPS. This is what we do all the time with matrix product operators, which has some problems, of course, but it's the way we can work with them efficiently. So at this level, we just treat it as a vector, and this vector is really like a product of maximally entangled states, because my identities as an operator are maximally entangled states as a vector. And on top of that, I can apply these exponentials, say one step of the evolution, which acts on the physical side, on one of the sides of the identity, and nothing on the other. But this is basically an MPS on which I acted with an MPO, and I can approximate the result. Or I can do it gate by gate, again, using the TBD approach. And I can repeat this as many times as I want, and then at the end, I will, in principle, find the rho of beta, the e to the minus beta h that I was looking for. Now, one problem if I do that is that in all these truncations, I didn't worry about the positivity of the result. And that's what I said before. If what I want to describe is an MPO that has to be positive, this is not going to happen. So if your truncation is large, this is going to be far from the true result. And positivity can be violated as much as I truncate. But in this particular problem, the purification is really the natural way to go. And it happens just for free, basically. Because if instead of computing the exponential of minus beta h, I compute the exponential of minus beta h halves, then what I have is basically a purification. And when I square this thing, or take the adjoint of this thing together with this one, except for the normalization, I will have a positive operator, which is basically describing my thermal state. So this is the standard way, I would say, of computing thermal states, the one that works best, and it's a very, very robust use of this technique. And actually, after you have that, you can do real-time evolution on top after putting some operators, and this is very interesting from the physical point of view because it gives you what is called response functions that somehow control, at least give you in linear response, what the reaction of the system is to perturbations and how it will thermalize and so on. So this is very interesting dynamical property. There are other methods to attack these thermal states, which also use matrix product states and so on, but have a different philosophy. So I'm not really talking about that. So I don't know. I didn't stop to ask for questions. There were a couple, but I don't know if there are any more questions now. If not, I give you some other ingredients in here. And since I cannot see my my slides, I will jump something, but okay. Okay. So another thing we can deal with is these open systems that evolve under some dissipation, so that suffer some dissipation. And in this case, this is real-time evolution, but it's a non-unitary one. So this is given. Oh, okay. Or the scenario I want to deal with in here is that given by a master equation, which is of the Lindblad form. And what happens after a long time of this evolution is that the state generically will reach some steady state. And we might be interested in knowing what is this steady state of our system, which is not isolated, but is interacting, like in a practical situation, is interacting with some environment. And so we are looking for the fixed point of this evolution. And that, although it is real time, it resembles very much this imaginary time evolution situation where we are just targeting the fixed point of something. And well, this has some uses. For instance, well, one can use this to do quantum computation, actually, encoding in the steady state the solution for some problem. So it's just interesting in general also from the practical point of view, because experiments have some dissipation going on. And you might want to know how things change when you change the parameters in your problem. So the idea is that we can approximate this steady state as a matrix product operator, and this can be done directly by doing the time evolution, in this case in the open system, so vectorizing the state and doing the same things that I was saying before, or variationally, just looking directly for the fixed point of this problem. I'm not. I think I'm skipping the details in here. I would just like to show you something else. So this is just how you vectorize the whole thing to deal with it in the same picture, but it's not so important. So the problem with real-time evolution that I mentioned before for pure states, this is a real one. It's a real problem. So the entanglement grows, and our state is not an MPS anymore. But still, one could try to figure out properties of out-of-equilibrium dynamic, because this is really very interesting, while keeping this problem somehow, going around this problem somehow. And an alternative to that is to, well, just give up the description of the state, say, as an MPS, and try to target on the physical quantities that are dependent on time and we want to compute. And one way is to think in a more general framework of like the observables that we want to compute in time as just a tensor network that we need to contract. So the contraction of the tensor network is giving us the expectation value, and we have different ways of doing it, or try to approximate. We don't have a description of the state anymore. We have just a tensor network for the observables. And the problem is, how can we contract this? And we know that in general, the exact contraction is not going to be possible, because even if we have a one-dimensional system, when you put time on top, we really construct a two-dimensional network, which has an extra dimension of time, and contracting that in general is not true. But there are different approximation schemes, and in some situations, one might be preferable to another. And the key is really some kind of entanglement in this tensor network, if we want to approximate things with this tensor network tool. So this tensor network that appears in here would be, for instance, just applying what I said before. You can start with your initial state, you can apply some steps of evolution, and then you have basically a two-dimensional tensor network that is not an MPS anymore. Well, it's an MPS, but with a large one dimension, that describes your time-evolved state. And then your observable is obtained by just contracting this thing with a joint and sandwiching in between whatever observable you want to compute. Now this is the problem. So there's no state anymore. This is the problem you want. And I'm not going into details very much about possibilities that there are. I want to mention, to make a small parenthesis here, to mention something that I completely skipped in these talks, but it's another way of using these tensor networks to deal with quantum many-body problems, and many-body problems in general, which is thinking of tensor networks like this one with no open indices to describe observables or, for instance, partition functions of, say, statistical mechanical problems. So, and this could be classical or quantum problems. So if you can write a tensor network that describes your partition function, then the issue is again to how to contract it. And there are tensor network algorithms that approximate this contraction, and generically they are called Prg approaches, which is tensor renormalization group approaches. The rough idea is some sort of coarse graining of the network in which you contract together a set of tensors, and you find a new tensor that describes this coarse grained tensor network. In general, if you do that, the one dimension of whatever tensor you have grows, but here is where the, say, algorithm comes in, how you choose the degrees of freedom that best represent your whole, or give you back the whole contraction. There are many references about that. These are some of the initial ones that started this Prg say, way of thinking or using tensor network. I haven't talked about that, but this is a ongoing activity on using tensor networks to deal with quantum many-body problems. So I think I'm just skipping this. So I have to jump ahead and just use 3 more minutes to tell you somehow why we are still so interested about this real-time evolution. So what I was going to say in here is just this intuitive picture why it is hard to describe this time-evolved state. And the intuition comes from a very, like, say, easy to understand situation where we can solve things exactly, which is that of freely propagating excitation. So if you start on a state, and then you perturb your system a lot, such that you are creating excitations everywhere. And these excitations do not so these are like quasi-particles. They do not interact with each other. They are free, but they appear like, say, a pair of like left-going, right-going that comes from one side, and they are traveling in your system with some speed and not talking to the others. So they are not colliding with each other or anything. So it's like a simple scenario. But what happens from the point of view of describing this as an MPS is that if you start with something which was local in here, then you are creating correlations that go longer and longer in distance as time passes. And of course, if you want to cut your system somewhere, you will have more and more of these pairs crossing this cut for longer and longer time. And that's what makes it difficult to describe the state as an MPS. But of course, it doesn't appear the same way if you do other things, like, for instance, evolving the operator towards the edges. It's like what is called Heisenberg picture time evolution. That doesn't solve the problems, but it gives you access to some case. And there are other strategies that I don't want to enter in here. So I'm just jumping ahead this and just going to the here. So just the idea is that there are different evolution algorithms. So the first one that I'm showing in here is approximating the state, say, as an MPS or a PEPS or whatever. And the problem is when entanglement grows, we know that this breaks. The other approximation that I mentioned is this Heisenberg picture, evolving the operators. And there are other strategies where we can just target the observables and just say, okay, forget about the state, and let's target the physical quantities that we want to describe. Why is this so interesting? So, well, it's so interesting because there is really a fundamental question related to these properties that Jens also presented yesterday, and it's that of thermalization. So the idea is that, so thermalization, usually when we talk about thermalization, we have in mind that there's a system interacting with some environment which has some temperature, and the system thermalizes to the temperature, like your cup of coffee or something like that. But in here, thermalization is thermalization of a closed quantum system. So it's basically, you could say, it's a question about where did that bath, that environment come from? Like if the whole universe is a closed quantum system, so when can we describe like the whole big system as a bath, as something that is in thermal equilibrium? And so the question is posed then for a closed quantum system. So we have a closed quantum system, it starts out of equilibrium, starts evolving, but we just look at local properties. So the question of whether it thermalizes or not refers to these local observables. So whether these local observables have some equilibrium values after some time, and the fact that they thermalize means that these equilibrium values forgot about the details of the initial state, and also that they correspond to some thermal ensemble, some statistical mechanics equilibrium ensemble. So for exactly solvable systems, this can be solved, but the problem with exactly solvable systems is that they have so many conserved quantities that the situation is non-generic. They do not thermalize to something that is just given by a temperature. They have a lot of constraints. And there is a framework to understand that. But for non-integrable systems, which are the generic ones, we cannot do exact solutions because they are non-integrable. And then here is where, well, there is some framework predicting that there will be thermalization, but it's a hypothesis. So if we want to check if this is true for a given system, it's not that easy. One can do it only for small systems. So here is where it is interesting to have numerical simulations of these things. And well, the problem, I'm just leaving you with this problem. The problem is what I just presented, right? So at the initial time, we have a very easy state, no correlation, a matrix product state, a product state. In the infinite time limit, we expect to have thermalization. So thermal states are well described by MPO. So we have something that is described well by a tensor network, at least at the level of local observable. But if we want to follow this evolution, our entropy grows linearly with time, the one dimension we need grows exponentially with time, and we cannot go through some intermediate time. And people call this the entanglement barrier. So you hit this barrier, your simulations don't go through. And well, this is sort of a challenge, like getting around this limitation by targeting the local observables, and it's something where different people are working on. Also, we are working on that, and there are different ideas to make small steps to get some more information about this dynamic. But that's basically what I wanted to tell you. So if you just want to take some message from these talks, it will be this one, like these tensor network states are these ansatz based on entanglement. And about the methods, you can think that they are quantum-inspired methods that describe quantum many-body systems. And well, regarding the algorithms, we have very efficient algorithms to find ground states, find thermal states, to do time evolution, but for time evolution, we know that there are limitations. And this doesn't mean we cannot use them, we can use them, but with some limitations. I don't know if the QR code works. Oh, okay, because I mean, of course, it's done for the Zoom, for the Zoom presentations, and in the big screen, sometimes it doesn't work. So these are some notes where basically everything I told about the different families and so on is contained. So yeah, if you find them useful. Also, you have a lot of bibliography there. There is some of the bibliography here, but if you have the notes, so you have a better bibliography there. And well, this is all I wanted to tell you in these talks, and thank you very much for your attention, and I'll be happy if you have questions.
Very much. Are there any other questions? One.
I think. Yeah, but he didn't ask the question. Thank you. Convex combinations of matrix product states. Yeah, probably you mean matrix product operators. So matrix product states are pure states, right?
It just seems like it might.
Okay, so about rank one, so you mean product state? Yes? Yeah. Mm-hmm. Okay, I don't know how much. So there is some things in this direction coming from the applied mathematics community, because they look at different tensor decompositions of the states, and they might have looked at that. There is also the possibility of, like, for instance, to describe these mixed states as, instead of a mixed state, to write an ensemble of pure states. So people have looked at that explicitly for thermal states. If you just have a sum of MPSs, then, okay, there's another scenario for open systems where people have also looked at that, which would be quantum trajectories, where you can describe the evolution of an open quantum system by sampling over the possibilities of, like, say, quantum jump. So that would go in that direction. In these cases, you have a limitation of how much entanglement you might describe. So there might be an advantage in doing the MPO description, because if you are looking at pure states and you have just a number of them, then you have an upper bounded quantity of entanglement that you can describe with them. And if your intermediate evolution goes through like a lot of entanglement, this might be better described by an MPO. But I don't know of a very systematic exploration of that.
Hi. Hey. Thanks a lot for the amazing overview. Thank you. That's super valuable, I think. I found really cool the connection to finite state automata, and I was like elaborating on Mari's question. Do you know how far this goes? Like, do you know what kind of states correspond to push-down automata or to linear bounded automata? Okay, and then the other question would be, and what you claimed, or like the results you presented, are they written down anywhere?
Yes, there is a paper by Cross-White and Bacon, I think.
Ah, yes, that old
but
paper.
That's the only one I know.
Still, yeah, I have. I know that paper. Yeah. Okay. Thanks a lot. That's super
Thank you.
cool. Thank you.
Other questions? Okay, I guess not. So let's thanks Mari-Carmen again.
Thank you.